Welcome to the deep dive.
Okay, let's jump straight into it. Today, we're looking at software development processes and agile practices. Really core stuff if you're building software.
Absolutely. And you, our listener, you've given us some great material on this.
Yeah, fantastic collection. Our goal here is pretty simple. Pull out the key insights, make them, easy to grasp quickly.
And we like that analogy in the sources,
Yeah.
thinking about it like a cookbook versus just winging it in the kitchen.
Exactly. Software processes are kind of like those cookbooks. They give you structure.
But like any recipe, sometimes you need to tweak it, right?
Right.
Adapt it to your own kitchen, your own project.
For sure. So yeah, this deep dive is all about understanding those different recipes, the different ways software gets built, from the basics up to the more, let's say, flexible styles.
And the mission, really, is to see how having a plan is vital, but being flexible, being able to adjust that plan, that's crucial for success.
Okay, let's unpack this, starting right at the beginning. Software development processes and practices, the building blocks. Right. So at its most basic, a software development process. It's really just how you organize the work. You break it down into distinct stages or phases.
And inside those phases.
Inside those, you have specific activities and tasks.
Mm-hmm.
Moving through these steps gives clarity, structure. Everyone knows what's happening. It's the big picture plan.
Gotcha. And that fits into the software life cycle, the whole journey.
Exactly. The life cycle is everything, from the very first idea, maybe on a napkin, all the way through development, release, updates, until it's finally retired.
And that can include smaller cycles for big updates too, right?
Oh, yeah. But today, we're mostly zeroing in on that initial creation phase, building something new from scratch.
Okay, so within that life cycle, we have phases. You mentioned those are like logical groupings.
Yeah, think of them as major stages. Common ones you'll hear about are specification, figuring out what needs to be built, then design and implementation. That's, the coding part.
And verification and validation, making sure it works.
Precisely. Checking it does what it's supposed to and what the users actually need.
Okay, phases are the big buckets. Down from that, we get activities and tasks. Can you give an example?
Sure. So let's take that verification and validation phase. An activity within that might be something like executing tests, pretty broad.
Right.
But the individual tasks to achieve that activity could be things like writing the test framework code, maybe designing the specific tests, then writing those test scripts, and finally running the tests.
Oh, okay. So tasks are the really specific, actionable items. That's where the actual work gets done.
Exactly. They're the smallest chunks you can manage. You complete tasks, that completes an activity, which helps complete a phase, and eventually you've got your software.
And these tasks produce work products.
Yeah.
That's not just the final software, is it?
No, not at all. It's everything produced along the way. Design documents, requirements lists, the actual source code, test cases, all of those are work products.
So the output of one task often becomes the input for another one, like a chain.
That's a perfect way to put it. And to do these tasks, you need resources. Obvious things like time, people, money.
But also technology, knowledge.
Right? All the ingredients needed. A task consumes resources to produce a work product.
Okay. And the people doing the tasks, the sources emphasize using roles, not names.
Yeah, that's generally good practice. Instead of saying, Steve will do the UI design, you'd say, the UI designer role is responsible for this.
Why is that important?
Well, it provides consistency. People might shift responsibilities or leave a project. Assigning tasks to roles keeps the focus on the required skills and activities, not the specific individual. Makes it easier to manage.
So roles like graphic designer, programmer, tester, project manager, product owner.
Exactly. Those define the job functions. A role performs certain tasks.
Okay, so we have processes, phases, activities, tasks, work products, resources, roles. What about practices?
Right. Practices are, well, they're the how. They're the strategies or techniques you use to actually execute the process effectively. Think of them as the smart ways of working.
Like estimating how long tasks will take.
Yep. Or holding daily stand-up meetings to keep everyone synced. Or having a really solid process for preparing effective tests. Practices make the process work smoothly.
They're like the techniques you use with a recipe.
Exactly. You could follow the recipe steps, but using good techniques makes the result better.
And a set of practices makes a methodology, like Scrum being an Agile methodology.
Correct. A methodology bundles together a set of related practices. And if those practices align with the Agile Manifesto's values and principles, then it's an Agile methodology.
So there's a clear hierarchy here. Process at the top, then phases, activities, and finally tasks.
Yep, that's the basic structure.
And tasks often depend on each other, right? You can't do B before A is finished.
Absolutely. Task dependencies are crucial. The example in the source was UI design. You generally need to figure out the visual layout before you program how the buttons work.
Makes sense. Otherwise, you're coding for something that might completely change.
Yeah.
Wasted effort.
Big time. And remember, tasks link back to roles, who does it, and work products, what it uses and produces.
In practices, they can apply just within one phase or across the whole project.
Both. Some practices are very phase-specific, like techniques for eliciting requirements during the specification phase. Others, like good project management practices, run throughout the entire process.
And the key thing seems to be flexibility. These aren't rigid laws.
Not at all. They're frameworks. You can, and often should, customize them, tailor them to your specific project.
Okay, solid foundation built. Now let's zoom in on the main software engineering activities. The sources group them into specification, design and implementation, and verification and validation.
Right. Let's start with specification activities. This is all about understanding and defining what the software needs to do, the requirements.
And importantly, this isn't always just a one-shot deal at the start, is it? Especially with more modern approaches.
No, definitely not. In iterative or parallel models, you often revisit and refine requirements as you go along. Your understanding evolves.
So what activities actually happen during specification?
Well, it starts with identifying the initial idea or need, really getting the why. Then eliciting requirements that's actively digging, asking questions, probing to uncover everything.
Then you have to write them down clearly.
Exactly. That's expressing requirements. Then comes prioritizing them, which ones are most important. Analyzing requirements is about checking for clarity, consistency, making sure nothing's missing.
Managing them too, keeping track.
Yep, managing requirements, organizing them, handling changes. And finally, formulating potential approaches, starting to think about how you might build it.
Really nailing down that initial idea seems critical.
It absolutely is. Everything flows from that initial understanding. Get that wrong, and you might build the wrong thing entirely.
Okay, next up, design and implementation activities. This is where the dev team rolls up their sleeves.
Pretty much. This includes designing the architecture, the high-level structure. Think foundations, walls, how rooms connect. Also designing the database, if needed, and designing interfaces, both user interfaces, and how different software components talk to each other.
And then the actual coding.
Right. Creating executable code, followed by integrating functionality, making sure the different pieces work together smoothly, like plumbing and electrical in a house.
Can't forget documentation.
Definitely not. Documenting the design and the code is crucial for maintenance, for future developers, for understanding how it all works.
And good practice as design happens before coding starts, right? Get the blueprint first.
Ideally, yes. Having that design plan makes the actual construction phase much more efficient and less chaotic.
Okay. Third group, verification and validation activities. Making sure it's right.
Exactly. It's about checking everything's on track and that the final product actually does what it's supposed to do and what users need.
So what falls under this? Testing, obviously.
Yep. Developing test procedures, creating specific tests, and of course executing those tests, then reporting the results.
What else? Reviews.
Sure. Conducting reviews or audits of the code, the design, the requirements. Also demonstrating the software to clients or users is key for validation, getting their direct feedback.
And you mentioned retrospectives.
Yes. Conducting retrospectives, that's where the team reflects on the process itself. What went well? What could we do better next time? It's about improving both the product and how you build it.
You mentioned verification and validation.
Mm-hmm.
What's the key difference there again?
Verification is more internal. Are we building the product right? Does it meet the specifications and design documents we created?
Right.
Validation is more external. Are we building the right product? Does it actually meet the client's or the user's real needs? That feedback loop in iterative models is crucial for validation.
Gotcha. Verification built right. Validation right thing built.
Essentially, yes. And those retrospectives are great for refining the process itself. Continuous improvement.
Okay. And running alongside all of this are project management activities. These happen throughout.
Continuously. From start to finish, it's the orchestration layer.
What kind of things does that cover?
Well, creating the process itself initially. Setting standards like coding conventions, how much documentation is needed, what done actually means for a task.
Risk management must be a big one.
Huge. Managing risks, identifying potential problems,
Hmm.
business, technical, resource risks, and planning how to mitigate them often results in a formal risk plan.
Estimations, schedules.
Yep, performing estimations for time and effort, which feeds into schedules. Allocating resources, assigning people, managing budgets, creating those schedules.
Measuring progress.
Right, making measurements, using metrics to track product quality, process efficiency, making sure things are on track. And just like with the software, improving the process itself is an ongoing management task, always looking for better ways to work.
Wow, okay. A lot goes into orchestrating software development.
Yeah.
So we've got the building blocks, the activities. Now let's look at how these get organized into different approaches. Process models.
Right. And the sources make a good point. These models have evolved, but newer doesn't always mean better. It's about the right tool for the job.
You wouldn't use a sledgehammer to crack a nut.
Exactly. A really complex process model can just bog down a simple project.
Okay, first up were linear models. What's the defining feature?
Sequential phases. You finish one phase, get approval, then move to the next. Generally, no going back. They work best when requirements are super clear up front and not expected to change much.
And the classic example is waterfall.
That's the one. Requirements, then design, then implementation, then testing, then deployment. Each phase flows down to the next, like a waterfall.
Pros and cons.
Well, it's simple to understand. Clear milestones and deliverables. Emphasizes planning and design early on. Can work for maybe well-defined outsourced components.
But the downsides.
The big one is inflexibility. It just doesn't handle change well, which is, pretty common in software. Testing happens very late, so fixing bugs found then can be really expensive.
And the client doesn't see anything until the end.
Right, which means what you built might not actually be what they envisioned. Big risk there.
Okay, then there's the V model. How's that different?
It tries to address the late testing issue. It's still linear, but it explicitly links testing activities back to the corresponding design and requirements phases, creates a V shape on diagrams.
So like for every design step on the way down, there's a corresponding testing step on the way up.
Pretty much. Verification happens against the related design or requirement spec. Still linear, still not great with change, but it does bake in testing more formally throughout. Client still sees the final thing late, though.
In the sawtooth model, trying to get the client involved earlier.
Yeah, that's the idea. Still linear overall, but it builds in specific points where the client reviews intermediate prototypes. That back and forth creates the sawtooth look.
Benefit being earlier feedback.
Exactly. Increases the chance you're building what they actually want. But it's still fundamentally linear, so major changes are still difficult. It's more for incremental tweaks based on the prototype review.
So linear models, easy to grasp, good for stable projects, but that inflexibility is a major drawback in many modern contexts. Early decisions really lock things in.
Yeah, it's that old manufacturing view of software which doesn't always fit. Software development is often more creative, more exploratory. But linear models can still be useful for simple stuff or parts of bigger projects.
Okay, contrasting sharply with that are iterative models.
No.
These repeating stages.
Absolutely. Looping back, refining things based on feedback. That's the core idea. Client feedback is expected, even welcomed, much more aligned with Agile thinking. Often, each iteration might have its own mini sequence of activities, almost like small linear steps within the loop.
The main example given is the spiral model.
Right. The spiral model cycles through 4 main activities in each iteration. Determine objectives for this loop, identify and resolve risks, develop and test the prototype for this loop, and then plan the next loop.
So each loop produces a better prototype.
Essentially, yes. The product spirals outwards in complexity and refinement. You learn, you adapt, you build upon the previous cycle.
Any downsides to spiral?
Estimating the whole project can be tricky, especially early on when there's lots of uncertainty across multiple future spirals. And it really leans heavily on good risk assessment, which takes expertise and resources. You need to be good at spotting those potential roadblocks.
Okay, so iterative is about loops and feedback. Then we have parallel models. How do they fit in?
Parallel models are also iterative, but they emphasize doing more things at the same time within a phase, more concurrency.
And the big one here is the unified process model, or UP.
That's the key example. UP is iterative, it has distinct phases, but within those phases, multiple activities and tasks can happen in parallel. Phases end with major milestones.
Can you walk us through those 4 UP phases, starting with inception?
Sure. Inception is usually short. The goal is just to establish the business case. Is this project worth doing? Financially viable? You'll outline some basic use cases, get a rough scope, identify major risks.
No iterations in this phase.
Typically not. It's about getting the green light. If inception drags on, it might mean you're overthinking it. It ends with the life cycle objective milestone, basically. Yep, this looks feasible. Let's move on.
Okay, phase 2, elaboration.
Right. Now you start digging deeper. You refine the core architecture, maybe build some technical prototypes, really investigate those risks identified earlier. This is where iterations do start.
So fleshing out the plan.
Yeah, refining requirements, creating key design documents like use case diagrams, class diagrams, laying the foundation for the bulk of the building work. It ends with a solid plan for the next phase.
Which is construction. This sounds like where the main coding happens.
Exactly. This is usually the longest phase, also done in iterations. You're building the software, feature by feature, based on the architecture and plan from elaboration. Detailed design continues, but the focus shifts heavily to coding and testing.
Still parallel activities within the iterations.
Oh, yeah. Design, coding, testing might all be happening concurrently on different parts. You build it up iteratively until it's ready for an initial release.
Then finally, transition. Handing it over.
Pretty much. Getting it to the users, getting their feedback on the real thing. This phase focuses on fixing bugs found in real-world use, maybe doing some final training or deployment activities, and planning for future updates. You might even cycle back to earlier phases from here if major changes are needed.
So UP allows for that parallel work within iterative cycles. Seems suited for larger, more complex projects where things can evolve.
Definitely. It allows the product to grow more organically. Now, we've mentioned prototypes quite a bit, especially with Spiral and UP. Let's dig into prototypes a bit more.
Okay. The sources listed 5 types. First was illustrative. Sounds basic.
Very basic. Think drawings, sketches, maybe a PowerPoint mock-up, index cards. The goal is just to communicate the core idea, the look and feel, get everyone on the same page visually without writing code. Storyboards, wireframes, that kind of thing.
Good for exploring early ideas.
Absolutely. Reading out bad ideas early, getting a common vision.
Next, exploratory prototype. This involves code.
Yeah, some working code, but usually focused on testing feasibility. Can we technically do this? Is this approach viable? You expect to throw this code away later.
So it's about learning, not building the final thing.
Exactly. Understanding the effort involved, maybe testing a tricky algorithm. Sometimes you might even fake the back end, have a human doing the work behind the scenes just to test the user interaction flow. How realizable? How useful?
Throwaway prototype. Also discarded.
Also discarded, yes. But here, the idea is often to build a functioning first version, maybe quickly and imperfectly, specifically to learn from the mistakes. What didn't work? What architectural problems did we run into?
So you build it, learn, then build the real version better.
Precisely. Use the lessons from the throwaway version to design a much more robust second-generation system.
Okay, the last 2, incremental and evolutionary, sound different. These actually become part of the final product.
Correct. This is where the prototype work does contribute directly. With an incremental prototype, you build and release the product in pieces, usually prioritizing the absolute core must-have features first.
So release 1 has the basics, release 2 adds more features, and so on.
Exactly. A series of releases, each adding functionality based on priority, sometimes called triage, must do, should do, could do.
And evolutionary prototype.
Evolutionary starts differently. The first prototype aims to have all the major features included, at least in some basic form. Then, subsequent iterations focus on refining and improving those existing features, making them more robust, more user-friendly, letting them evolve.
So the key difference. Incremental adds new features over time. Evolutionary improves existing features already present in the first version.
That's the core distinction. And like you said, the big shift is that effort put into incremental and evolutionary prototypes directly contributes to the final product, unlike the first 3 types where the value is mostly in the lessons learned.
So prototyping helps visualize, get feedback, make smarter decisions, fits right into models like Spiral and UP.
Absolutely. Illustrative prototypes early on, maybe in Inception. Then subsequent iterations might use incremental or evolutionary approaches. It's all about gaining feedback to make informed choices.
Okay, building these incremental or evolutionary prototypes sounds good for feedback, but getting them out there. The sources mentioned continuous delivery for that.
Yeah. Prototyping gives you something to show, but continuous delivery, or CD, is about automating the process of getting those working versions tested and potentially released much more frequently and reliably.
So it's not just building iteratively, it's delivering iteratively with automation.
Exactly. The aim is to always have a version of the software that's built, tested, runnable, and potentially shippable. When a developer checks in code, it automatically kicks off a pipeline. Build, integrate, test, package, maybe deploy to a test environment.
Super fast feedback loop.
Very fast. And importantly, it doesn't mean you force releases. Unready versions stay in internal or test channels. You might have different channels: developer, test, staging, stable, with different levels of polish and different feedback expectations.
And this slots nicely into iterative models like UP, especially during construction.
Perfectly. You finish an iteration's worth of features guided by your incremental or evolutionary approach. You've done detailed design, coding, written tests. Then the CD pipeline takes over.
Automating the build, integration, testing.
Right. Automated tools handle compiling, linking, running unit tests, integration tests, packaging it up, deploying it. For big projects, that build automation needs to be smart, only rebuilding what's changed.
And the goal is a releasable candidate at the end of every iteration.
That's the ideal, yeah. It means even if the project stopped tomorrow, you'd have a recent working tested version. Plus, all that frequent integration and testing really boosts quality, catches problems early.
The sources mentioned the Microsoft Daily Build, like a one-day iteration.
Kind of, yeah. An extreme example of continuous integration within the construction phase. Everyone integrates their code daily, it gets built and tested automatically, ensures everyone's in sync, catches integration issues immediately, huge quality benefit. There were even incentives for successful builds.
So continuous delivery sounds powerful. Regular feedback, higher quality, early issue detection. But maybe overkill for small projects. Setting up all that automation takes effort.
It definitely does. There's overhead. For a small, short-term project, a simpler linear process might genuinely be more efficient. But for large, complex systems, those linear models just don't cut it, and something like UP with CD becomes incredibly valuable.
Which brings us back to that core idea. Process is a tool. Choose wisely.
Absolutely. There's no silver bullet. Iterative isn't always better. Parallel isn't always needed. Sometimes linear is fine. Sometimes you mix and match elements.
Do what works best for the project, the team, the context.
That's the key takeaway. Be pragmatic, be adaptable.
Okay, well that wraps up our deep dive for today. We've covered a lot. The nuts and bolts of processes, activities, tasks, the different models like waterfall, spiral, unified process, the role of practices, agile.
And digging into prototyping and continuous delivery. Hopefully, breaking it down like this has made it digestible and useful for you, our listener.
Yeah, we aimed for that quick but thorough understanding without getting bogged down. So a final thought to leave you with.
As you think about all this, consider projects, maybe even outside software. Where do structured linear approaches work best? And where does that flexibility, that iterative refinement really shine? It's interesting to think about how these concepts apply more broadly, isn't it?